Okay, so good morning, everybody. We're 2 minutes late already. It's a bit chaotic today because I guess most of you were in the globe for the keynotes. So welcome to the first session in Auditorium C. My name is Enrico. I'm the guy operating the Ceph clusters here at CERN, and I'm on stage with my good friend, Jose.
I'm the cloud technical lead that is in charge of the cloud infrastructure service. That's basically how we are offering Ceph at CERN.
Right, so let's just get started. So welcome to CERN. It's beautiful for us to have you here. It's almost emotional to me. As you know, we are the biggest particle physics laboratory in the world. We have the honor and the responsibility to operate the biggest particle accelerator and collider, which is the LHC, Large Hadron Collider. We have 4 experiments along the accelerator facility: ALICE, ATLAS, LHCb, CMS, and just for you to get sorted where we are in the bottom part of the image, pretty much in the middle. So when you think about our particle accelerator, this is not something that lives on the surface. We had to dig a tunnel to make it happen. It's 100 meters underground, and actually the accelerator of particles operates inside this gigantic blue pipe that you see in the picture on your left-hand side, where you basically have 2 pipes made of superconducting magnets, and you have 2 beams of particles which are getting accelerated and steered by means of collimators, such that at very precise points of the accelerator complex, they crush one into another, and then we study the result of this collision and of the interactions. We do that with detectors, which are placed in the 4 main experiments. You have pictures of them here, so it's 4 experiments, 4 detectors, 1 detector per each experiment.
But we do not only have 4 experiments doing collisions, we have many more experiments on site that basically study different parts of physics. We have the alpha experiment studying anti-hydrogen. We have the Isolde studying isotopes on radioactive elements. We have also the neutrino platform studying these neutrino particles that are very known, but we don't know much about how they interact with the rest of the particles. But they also have an experiment in the International Space Station looking for antimatter and dark matter. And all this data that comes to us in IT, they get piped into the 2 data centers that we have, mainly to cover 3 main tasks. We need to reconstruct all the collisions that happen over there, and looking at the particles that are as the sub-products, we need to reconstruct the paths to know where they're coming from. We need to store this reconstruction and all these events that happen over there, so then the physicists can read those data and do their analysis. And we are also distributing over the World Wide Web, over the WLCG, over the tier 1s and the tier 2s, in which the physicists can run their data. And for that, we operate 2 data centers, one in Meran, another one in Prevesan, although we have many more over the years. And we are operating around 11,000 servers, almost an exabyte of data stored on disk, almost 0.7 exabytes of data in tape, and hundreds of services on the setup that is basically for the working of the lab.
So just to give you, in a very nutshell, a slightly better understanding of how Ceph and OpenStack supports CERN missions, you have already learned that everything satellites around colliding particles and do that with detectors, such that we can characterize what's going on. So if we put the detector in the middle of our picture, as you can understand, these detectors are very specialized machines. We have a lot of application-specific integrated circuits design going on at CERN. All of this is developed in-house, and it's done by means of HPC clusters using CephFS as a backend storage. When the accelerator comes into operation, a lot of work goes into controls and monitoring. Monitoring is actually done in a very special way. The beams department that operate the accelerator complex produces hundreds of PNGs every 500 milliseconds, just reporting the state of the accelerator complex, and this is pushed to Ceph Rados gateways, to Ceph object storage, again, as PNG images, which are then projected and shown all around the organization and in the control rooms. A lot of data comes out of the detectors. We have a lot of storage on disk. We also do a lot of storage on tape as a safety copy and for posterity. We have a CERN tape archive service that was developed in-house that uses Ceph, particularly Rado's object store, for some of its internal state keeping and management of the service. And last but not least, there is a lot of data to be analyzed that, as Jose just mentioned, happens across the WLCG, which is a congregation of hundreds of sites around the world to which we ship the raw data, but we also ship software stacks such that scientists and researchers on their side can process the raw data. This is done via a specialized service which is called the CERN VM file system that uses Ceph object storage, and then we also have a global HTTP-based CDN which largely lives on OpenStack. You can also volunteer your CPU cycles if you wish from your desktop machines or your laptop. This is done via Boink, which uses CephFS to host the data that has to be shipped to the clients and collect the results that come back to us. Now, where Ceph and OpenStack actually really shine is in supporting IT needs. I'm not going too much into the details of the list here, but we are operating the infrastructure that supports the entirety community of users that we have at CERN. It's roughly 9,000 people. So every single thing that we do has to be very controlled. We have to be very precise and has to be deliberate. We cannot take the risk of operating our services in an unreliable way, because this is very visible, very impactful, and it means that someone around the organization will not be able to execute his work. So we use our infrastructure to deliver IT service within the storage group. We also use it to provide other storages which are not strictly Ceph, like AFS or NFS filers. We have an ongoing project to replace Microsoft DFS with some CephFS with Samba gateways on top. And we have a renewed interest in backups for RBDs, for FS. We have a dedicated S3 endpoint for this, which is optimized for the use case. And if you are interested in discussing how to make backups properly, we have a bird of a feather session tomorrow afternoon at 5:30 in the auditorium just next year by my colleague Abhishek, that will walk you through our plans and our pains in doing CephFS backups. So this is just a picture to show you with headlines our Ceph cluster fleet. We operate objects, blocks, and file system. Overall, we have just reached the bar of 100 petabytes. We're very happy about this, and we're happy to celebrate this milestone with you. In production, we primarily use Pacific and Quincy. We are also investing some time and effort into some more exotic configurations of Ceph, like stretch clusters for CephFS and RGW multi-site. And for these ones, we actually use Reef. So this is the outline of our talk today. Jose will talk about Ceph and OpenStack at CERN. Then we will share about the new data center that was just built. And then I will conclude with a few more technical details about cross-data center, even more available storage. So, Jose, off to you.
Thank you. So for all the storage that we provide through Ceph is kind of shown to the users via OpenStack. So I'm the cloud technical lead. I'm in charge of the cloud infrastructure service. That is basically the cloud that we build over here is based on the OpenStack framework that provides compute, storage, and network resources to users on demand. We started with the project in 2012 with a series of pre-releases to kind of fine-tune the setup and make it kind of production ready. And in July 2013, it was like it reached the production level, and since then we have been upgraded in place. So it means that we have been running the setup from Scientific Linux 6, CentOS 7, RHEL 8, and now we have the whole fleet in RHEL 9 and Alma 9. It's based on the Red Hat distribution of OpenStack with a couple of patches to integrate it on top on our setup, and it's like fully available. You can see the code that we are running is in the repos is publicly available to users. We have 2 sites, one in Meran that is like, I saw after, and another one in Prevesa. And for the ones that are savvy on OpenStack, we are running the yoga release. And I'm putting there a plus because we have two services that are running in set release already. And it's a way for us to expose resources to users. So basically, the framework is a set of microservices that each of them, they do a kind of a function. So we have services dedicated to provide virtual machines, to provide physical machines, to give you load balancers, to give you certificates, and so on and so on. And then we have the ones that are highlighted in red are the ones that are tied to Ceph. So it means that whenever you ask for a virtual machine, the image is in a Ceph RBD, stored in a Ceph RBD. Whenever you add an additional disk on one of the VMs that you're going to provision, this is a single volume that is backed by RBD images as well. If you have access to file shares, it's the same story. We have an vanilla tokens with different CephFS clusters that are providing the access to those CephFS shares. But we also have more components. And it's our kind of single pane of glass to offer resources. Everything that goes through us is through, like we offer through projects in which the users can request quota. And in this example, what we have is the kind of the perspective for storage. They can have access to many different volume types. Each of them have their own quality of service associated to them. So as you can see on the top, we have prepended with CP, because those volume types, they are backed by diesel generators, so they can stay up if there is like kind of a power cut in the data center. So for critical applications, that are the ones that you may want to have access to. Then we have the next part of the naming convention. You see different, like a standard, IO1, IO2, IO3. Those show the kind of the quality of service that the users can get from those. We get 100 IOPS if it's backed by spinning drive, it's backed by flash. So people can choose on these quota requests. And then also we have added backup. So now we can do volume backups also as well. If we look at the stats of the service, we have, like, as I said, we have around 11,000 servers managed by OpenStack, physical machines. And among those, we have 1,800 hypervisors running on top, more or less like 15,000 virtual machines that are running on the setup. Again, we look at the picture on the storage side, you can see that we have almost 4,000 volumes, 2.3 petabytes of storage using block devices, 2.6 petabytes of use storage using file shares, and also object store with 250 terabytes of data. And all this information is centralized because we want to have a kind of a picture of how we are using this data, how we're using these resources. So we aggregate all this information, and as you can see there on the slides, we have the overview of the utilization in terms of physical resources, of course managed, over time, because we need to have a kind of a view of how the resources are used in order to kind of order new hardware, in order to provision more disks for the Ceph clusters. And this is kind of the view that we and the capacity planning officer is looking at to kind of give an overview and plan trends. So if we go back in time and we find kind of the reasons why we built the Prevesa data center, it was mainly driven by the enormous amount of computational resources that the high luminosity LHC will ask us to provide. So the LHC that Enrico was showing up was like the the extension will produce 10 times more collisions. 10 times more collisions is like 10 times more particles to track and then to be reconstructed. So it means we are kind of giving kind of a generational gap that we need to cover. And for that, we cannot only kind of rely on the CPU manufacturers to kind of make CPUs faster enough. We need to have more, but also look into new architectures and new paradigms to see if we can cover the gap with those technologies. Things like GPUs, things like ARM resources, we are exploring every single option that we have there. And for that, on the cloud service perspective, we need to be flexible and adaptable. We do have already ARM resources on the pit that people can use. We have GPU resources, and we need to be more, as I said, more flexible. at the same time, give us another opportunity to look at one of the things that it was always like left behind, that is like disaster recovery. What happens if it's like we get a flood on the 513 building, and then we lose the capacity? We need to keep running. So then, for that, we have the new site has dedicated space for disaster recovery scenarios, in which we are kind of allowing our clients, services in IT, in services all the places in the laboratory to run their applications on top of us. And for that, we need to enhance the building blocks that we have in infrastructure, not only the compute part, also the network, and also the storage. So we have two sites. One that is extremely old, that is built in the 70s, originally constructed for mainframes, not the kind of equipment that we have right now. But then after that was like refurbished. So then we have PC farms there after, and now we have a rack-based setup in the old Megan data center. While the other side, we have the new flashy Professor site that was mainly built with all the things that we were learning over time. And this is in operation since February. They are not so far ahead, so it means like if we are hit by an asteroid, it needs to be super small. And we have pretty much amount of fibers between the two sites to maintain kind of a pretty nice 10 terabyte line between the two. And it's like pretty quick to get data there. When we start with the construction, we decided to go for a complete independent setup. For kind of business continuity perspective, you want, at least on the service that I manage, this is a cloud service, you want to be as independent as possible, so that both sites operate independently. So it means like if we lose one, we still have the other, running, control, and being able to create machines and access to resources. Handles any disconnection in between, and you don't need to have a third entity to decide which is the one that stays up. We use the resources, the virtual machines, and the hypervisors that we have on the Megan site to create the control plane for the new site and onboard the new hardware. And once we have the hypervisor, we just move all of them there, so it's now fully independent. In the older side, the cloud was grown organically, and then the things we were adding things on the fly, not looking much at the physical constraints we have in setup. The PDC, actually, we did the other approach. It was like we start from scratch for the physical constraints, and we are exposing to users what we have behind. So it means like we have a single floor, single AZ, because it's the unit that shares cooling, power, and network. So it makes sense to have it as a single AZ. But then it's like to allow people to move things, workloads around. Basically, we have server group policies that allow to distribute machines around, so then the users cannot, if there's like an event on a rack, they are not getting affected. We started from RHEL9, and for Ceph, Quincy, and Reef, that Enrico will say after, and we started with Yoga. It's not the latest and greatest. It was the first of the releases that was supported in RHEL9, but at least it was like a step ahead of the components that we have. And the idea was to match after, so that we only need to maintain one version. And we were looking at every single constraint that we have, try to sort it out, and learn from the kind of running a setup for more than 10 years, and try and apply all these learning experiences into the new setup, so we start from scratch in a with a good base. And what users see is these two entities they can access that are all independent, but to make our life easier, basically we synchronize some of the things like ACLs and the images to make the life of the users simpler.
So as Jose just mentioned, for us, the fact that we have a new data center is a major reboot. It's a major opportunity to do things right, learning from experience. So the first thing that we have tried to cash in was physical infrastructure. So our old data center was built in the 70s. It was organically grown over the years, which means that over time you accumulate technology debt. You don't have the proper hardware placement, or at least it's not ideal. So for designing the new computing center, we actually went to the whiteboard and we have tried to make it right. So we have tried to consolidate our unit of work as one rack, where you have some compute hypervisors for OpenStack and some Ceph storage. And then you just replicate over and over this single unit if you want to add more capacity, storage-wise, or if you want to add more compute power. We have a top-of-rack switch in every single rack, which is very nice because it helps you a lot in defining the failure domain, for instance, in Ceph crash, and we have redundant power feeds everywhere. In terms of hardware, we have primarily 3 main breeds for what concerns Ceph. We still use a lot of HDDs for capacity cost benefits. These are hosted in high-density JBODs, which are then connected to 2 head nodes. On the head nodes, we have some NVMEs for the block DBs of the OSD journals, while we have also a full-flash breed, which is purely NVMe 1U system. In this case, it's hosting 10 7.68 terabytes NVMe units. And also, we operate CephFS at scale, so a bit of dedicated hardware for the MDSs is needed, some CPU, some memory, and some decent NVMEs, not a lot of capacity, but speed is rather useful for the metadata pool. On OpenStack compute, we have quotes, slightly different architecture with respect to what we are used to operate, because these are all single-socket AMD processors with almost 1 terabyte of RAM on board and 4 terabytes disk redundant, because typically we prefer to boot VMs from the local disk instead of booting from volume. We have some use cases for which we still boot from volume, and this is hosted on Ceph. Second point on which we want you to learn from experience, CephFS metadata scaling. So we operate CephFS at scale. The busiest cluster that we have, it's roughly 500 million inodes. We have multi-active MDSs. Going multi-active is actually quite easy. You just crank up the number. The problem is, how do you balance metadata out? There are different policies according to which you can do this. We use a lot of manual pinning. It works, but it doesn't really pay off over time, especially if you have a lot of churning, like people deleting and recreating shares. They lose the pin. They go to MDS 0. The result is that MDS 0 is always extremely busy, and the others are pretty much doing nothing. So it doesn't pay off. We have used the dynamic balancer in the past. It's suboptimal for our workload because you have a peak on an MDS, then you export some emeta blob to another rank, and then that new rank becomes the newest, most busy MDS in the cluster, so this goes over and over, and you just burn a lot of CPU cycles just to balance it out. It doesn't work. So we disable that. We have no experience so far with ephemeral pinning. It's the next thing we would like to look into. We're just not there yet. Ideally, what I would like to do is not go multi-active, because this brings a lot of additional complexity in operations, in recovery. It's a bit different to operate a multi-active MDS setup. So it is good as far as you are able to keep your file system small enough such that one single active MDS can keep up with all the work. So we're actually thinking of looking into multi-FS as a solution to this. Instead of spreading over horizontally over a number of MDSs, we spread it over horizontally over a number of file systems, each of those having one MDS active only. We're just not there yet. We just know that what is going to be crucial is the fact that OpenStack Manila has a key role into this, because it will be actually the component that somehow protects our customers for all the complexity that we manage in the back end, and it's the piece of software that decides where the new share being created is going to be allocated, on which file system. So you have to basically come up with a metric that is representative enough to say, okay, I'm balancing out my metadata operation, but this is not necessarily obvious how to do it, because it changes over time, it fluctuates a lot. So there is a bit of work to be done on this side, but we're very curious if any one of you is facing similar issues or would like to take a look into this together with us. Last thing, more user-facing, is we're trying to make the life of our users as easy as possible. In the past, we have been exposing the full complexity of the infrastructure to other service managers in IT, but also to end users, which are not necessarily IT specialists. And this creates a lot of confusion, because maybe you have multiple clusters providing block storage, providing the same QoS of block storage, and they just see the whole list, and they do not necessarily, they are a bit confused of how much quota do I need, where do I need it, why should I update this field rather than this other field in the OpenStack control panel. So we're trying as much as we could to hide all of this by basically asking them three main questions. Where do your VMs and your data should be, in which of the two data centers that we operate? What storage type do you need? Is it a file system? Is it objects? Is it blocks? And what is the quality of service? Quality of service is typically challenging from our operational perspective because everybody thinks that their application is extremely critical, extremely important, needs the best gold-plated hardware we have ever had. And so there is a sort of a trade-off between what they think they need, what they actually need, and what we can provide. So negotiations are going back and forth. We are operating infrastructure with the concept of availability zone. This is helping us a lot with RBD. We're already using it there. We would like to do the same with CephFS. It's a sort of yet another layer of indirection that buys us a degree of freedom to better spread out things and operate, but it's not necessarily something users would need to know, not let's say the average user that just wants some storage and use it. Of course, we are still exposing APIs such that users, power users that really know how the infrastructure is deployed and how they want to build their application on top of our infrastructure, they could use it because maybe they say, okay, I can architect my application in such a way that if you have 3 storage availability zones, I use all 3 of them, and then if any of these is down, my application is still alive, and this is definitely a benefit.
Then, as I was saying, we're kind of working to start. We started with the premise side in a certain version of OpenStack and a certain version of Ceph, and what we have been working the whole year was basically align it. So it's like, as you can see there in the animation, we were kind of jumping some releases on some components. This is API based, and then the one that goes slowly moving is basically the hypervisors that were migrating to EL9 once we update the service to Yoga. Basically to align them to have one single version to maintain, because it's like for the kind of the team effort, it's like one less kind of thing to check. What does it mean in terms of operations? Like we are running 2 sites in parallel with 2 versions of pretty much the same version, but it's like 2 services of pretty much everything. And what we have in terms of Ceph, we have Ceph clusters independent for the images, as I said, the RBD volumes, the file shares, and also the object store that we need to test, validate in every single upgrade, and maintain it over time so users can do their work irrespectively, so they can consider it as production quality. And for that, we are probing the infrastructure every hour, and you can see there the stats of everything, every single operation we are running on the 4 setups in parallel to validate that users can create machines, can create file shares, can extend, can do ACLs every single time. But then on our side, we need a kind of single entry point. We have the same monitoring to have a kind of an overview of what happens on both sides. As I said, we're probing both sides to validate. We spend a huge amount of effort automating everything to minimize our kind of workload, because the team is exactly the same. I have exactly the same number of guys. And then for what is the kind of the end use perspective is basically this is like through quotas. They can access all the shares they have there. They need to justify why they need the kind of the fast I/O for their super important application. But even though this is a kind of a quota request that comes to us, and then the capacity planning officer with the overall picture of the kind of the growth of the service can do the kind of the assessment. But then there are still cases in which we are not covering with a kind of a threat with these 2 independent clusters. And Enrico will continue with that.
Yeah, so let me just introduce this last part. This is actually a gigantic hook that we are throwing at the community to understand what we're doing, what others are doing, if we can learn from experience, if we can share experience, because community is essential for us to be sure that we are on the right track, or maybe learn from some others' experiences and vice versa, and openly share the knowledge that we are accumulating as Ceph operators. So as Jose was mentioning, having 2 data centers is nice. Having 2 data centers which are fully isolated one from the other is good. But it doesn't necessarily cover everything that you want to do. If you take an application perspective, there are primarily two types of applications. There are things like Redis or MongoDB, which have onboard replication capabilities. They do not need any shared storage. They just go replicate, like deploy as many copies as you want. Everyone is running on its own storage, and you're happy. These are perfect. These are excellent because we do not have to do anything on top of those. The most challenging applications are actually belonging to the second category, and we have many of those. They are not so refined to do replication by themselves, and we typically get questions like, oh, I have this CephFS share with 100 million files in. I would just like to rsync everything over the second computing center. Do you know of any magic flag that does it faster? And this is typically quite problematic because the MDS has to go start every single inode, copy it over, you trash the LRU cache. It's a challenging thing, and maybe you have to do it daily, and maybe you have to do it with some time constraints like overnight when activity is low, et cetera, et cetera, et cetera. So this is precisely where we think that the infrastructure could help some of the use cases that we have. And we are primarily looking into Rados Gateway multi-site and CephFS stretch clusters as far as consistent storage spanning the 2 data centers is concerned. So let me just briefly introduce what we're doing with Rados Gateway multi-site. We have a rather traditional multi-site configuration. We have 2 clusters in the 2 data centers running Reef, 1 zone group, 2 zones, full replication. The main zone is read-write. The secondary zone is read-only. I will explain you why. We have dedicated groups of Rados gateways. We have the ones serving client traffic. These are actually integrated with OpenStack Keystone to validate the key pairs, and they have a traffic ingress. This is sort of a HNA proxy, if you're not familiar with traffic, that does a few nice things for us, like TLS termination, health checks, and the failover. The failover is not obvious. Like if you take a look at the picture here, when everything goes fine, everything is up and running and available, you have your client that goes through a first let of load balancing, DNS round robin, very simple. Then it goes to any traffic front end that you have, and if the main zone is up and running, they follow the green lines, so they go, the request is served, read-write, everything is fine. The problem with the failover is that traffic immediately realizes if the main zone is not available, it would redirect the requests to the secondary zone, which is configured to be read-only. Why? Because if the main zone is down for a long time, then you will end up having objects in the secondary zone, not yet replicated in the main one, but traffic would switch it back to the main one as soon as it realizes that the Rados gateways are active again. So you may end up having inconsistencies, and in the event of a real failover, because something really went horribly wrong, we much prefer to have manual control on this and do a manual failover of Ceph Rados gateways and reconfigure our traffic front ends to say, okay, what was secondary for you, now it's main, and it's used to serve read-write requests. We have a second set of Rados gateways purely for sync client traffic. So they just run Beast as a front end, and they only take care of synchronizing objects across the 2 regions. Our experience so far was so-so with Quincy, pretty good with Reef, especially as far as resharding is concerned. Not really going into the details here. One thing that for us is missing is some sort of load balancing and fairness for the synchronization traffic, both metadata and data. We have observed that typically there is one Rados gateway taking all the logs on all the shards, so the others are really not cooperating with the sync. They are just there for higher availability in case the Rados gateway that has all the logs goes down for any reason. This is apparently fixed. I think it's actually in Squid, but it has not been backported to Reef yet. And a nice operation insight that we had one day was when we have deleted the entire zone group. Because you fiddle around with the cluster, you delete, create, minus many things, and then whoops, you hit enter, and your zone group is gone, and it's relatively problematic. The data is there. You say, okay, how do I bring it back? I create a new zone group, which gets a new ID, so all Rados gateways are telling your clients, oh yeah, I know what you're talking about, but this for me is moved permanently, because the IDs of the zone groups no longer match. So we basically edited the JSON manually, and we fixed it with set in file, and everything continued to work nicely. To me, it's one of those comments like, minus, yes, I really mean it. Whenever you want to delete something, I think it's a nice protection mechanism. Monitoring of multi-site is not obvious. I was very happy to hear about things moving on with Squid and Tentacle. At the moment, we have a custom setup which is based on some monitoring infrastructure with Prometheus and Grafana that we already have. What is not obvious is actually to keep track over time how if things are aligned, what is lagging behind, if you have synchronization errors, if this is data, if it is metadata, if you have some stuck syncs, etc., etc. So we have a Rados gateway exporter that basically watches on user stats and bucket stats, these kind of things, just to have some counters and make sure that the counters are good on both ends. And we also have some custom tooling which are basically constantly checking the shard sync status and reporting on this. Next one, last one, stretch clusters. These are very interesting for us, especially for CephFS. Up until very recently, you had to decide whether you wanted to stretch or not. It was typically a one-way thing. Once a cluster is stretched, it's game over. It will be stretched forever. So you really have to think about it if you want to do it or not. Now there is a PR out. I don't think it's in any of the main general available releases that allow you to undo the stretching and go back to an unstretched situation. So thank you very much for everyone who has worked on this to make it happen. We are thinking about where we want to put our data, if the two data centers should be precisely identical or not, where to put the MDS, should they follow some affinity that they have with I/O or not. In this case, you can actually abuse of an MDS flag, which is MDS join FS, and basically promote the MDSs with MDS join FS in the data center where you want them to be active. But as I was saying, this to me looks as sort of an abuse. For instance, the monitors, they do have a location flag, a location parameter. I would be very happy to see the same with MDSs. One thing which is absolutely not obvious to us is where to put the tiebreaker. Documentation says you could put it in the cloud. We are the cloud. So if you just look at the picture, this is a sketch of our network diagram. You would like to put the tiebreaker precisely between the two core routers to have a perfectly symmetric view of the two networks and of the two data centers, but clearly we cannot do that because there is no useful hardware there. It's purely network equipment. We cannot. So we're still scratching our heads around that. Network is not the only concern that we have, is also power redundancy and some other aspects. If you're playing with stretch clusters, please let us know. In the past, we have had, not necessarily with stretch clusters, but in general, some problems with OSD flapping because of networks being flaky. So we keep at hand a couple of tunables in case things drift away. Another thing that exists in the kernel clients is 5.8 are some parameters and flags to say where the client is and make the client learn to which OSDs it should read against crash, purely based on the distance in the location. This is not much of a problem to us because the two data centers are close enough. We have bandwidth, we have very low latency, but it's still nice if you want to avoid every single time to have a round trip or to fly all the bytes all over just because you don't have something properly configured. We're late. Closing remarks. We're hiring a junior storage engineer for Ceph, specifically to work on AI/ML workloads. If anybody of you is interested or you know somebody who could be interested, we have a full job description on Smart Recruiters. If you click on the link, it will tell you that the application deadline is over. Don't worry too much. Come talk to us at the coffee breaks. And, okay, a little logistic thing. We are in the Science Gateway. It was already mentioned today. Sorry, it was already mentioned today in the keynotes that we have exhibitions privatized from 5:30 to 7 p.m. tonight, and it's actually just here. So if you walk out that door and you take a ride, you will see a gigantic glass corridor, and this is precisely where you want to be tonight at 5:30 to have free access to our visits and our exhibitions. Thank you for being here, and thanks to everybody who has contributed to Ceph and OpenStack at CERN over the last
10 years.
10 years. Thanks a lot. So we're happy to take questions. Now, I don't precisely know when the next session is going to start. I think it's in 5 minutes. So maybe we have time for 1 or 2 questions, but we're very happy to talk to you offline also if you wish. Talk to us. one there. Do,
repeat the question.
Yeah, okay, so so the question for the recording is, one single MDS is good enough for a small cluster. How do you define small? Yeah. It depends. It depends on many things. It primarily depends on your workload. We have clusters, CephFS clusters, which are specialized for HPC, or they are specialized for Microsoft DFS replacement. And they are all relatively small in terms of inodes. And I think that we have MDS cache memory limit set to 64 gigs, and you can cache pretty much many things. The workload from which we suffer the most is typically backups, because people want to back up many things. They have to start a bunch of inodes, and typically these inodes may not be in the cache. So the MDS will actually spend a lot of time just loading from the metadata pool, and then entries will be kicked out again from the LRU. So I don't have a precise answer to when small is small enough. This actually depends on the resources that you have, like hardware that you can throw at the MDS, and it depends on your use cases. For us, it's actually essential to get to know at least the most precious use cases that we have. Which is not necessarily obvious, because our infrastructure is free for use to the entire organization. So in the vast majority of cases, people just come along, get some quota, and then we never hear back from them, which is excellent, because it means that things work, but you lose a bit of control on your use cases and your customers. Okay, let me close it here, but we're very visible. We have many badges. Talk to us.